Well, good evening and welcome to our final class meeting, I suppose, for MT225. There's no real formal lecture this evening. We've finished all the content that we're going to go over in class. The purpose tonight is just to remind you of some of the upcoming deadlines and to take a look at any questions you might have, or to just kind of take a quick spin through the posted sample exam number 3 and give a few informal tips and tricks on maximizing your score. So let's see here. We have some due dates here. Homework 9 has been returned. So if you submitted a copy for homework 9, you should have gotten that back by now. For the most part, went just fine. Just a couple of little errors here and there, mostly with calculating areas. So be careful with that. Check the solutions. Make sure it looks, make sure you understand how to find the areas in, say, for example, hollow tubes and things like that. Homework 10, the bonus homework assignment on beam deflection has been posted, and that is due on Wednesday. And just before the exam, I'll open up any questions you might have on that in person at the hangar on Wednesday night, because Wednesday night is our third exam. That's at 5 p.m. So remember, 3 index cards max, 4 inches by 6 inches, and I will be providing food. And then we do have our final exam 1 week later. That is comprehensive, meaning it covers everything from the beginning of the semester. So I'll be posting probably Wednesday night while you're working on the exam. I'll be selecting and posting a prior final exam for you to take a look at. So I'll post that and the solutions. And so that sample homework 3 has been, or sample exam 3 has been posted. So let's see here. Phil, do you have any questions before I take a look at the sample exam?
No.
Okay. So let's see here. Let's go over and take a look at the sample exam. Let's see here. There it is. So this is the exam I posted, which is from way back in May of 2016, almost to the day though, May 4th instead of May 5th, back 5 years ago. Let's see. So problem 1 is all about figuring out stress. So thing to remember with this one is the definition of normal stress. So normal stress is the force divided by the area, the cross-sectional area. So what we've got here in part A is a rectangular plate. So it's got a cross-sectional plate area. It's a rectangular cross-section. It's 2 inches high and 25 inches wide. So that's a pretty significant plate. And we're putting on it an axial load of 250 kips. So to find the stress on that, we just find the area of that cross-section. Now, to avoid making a mistake here, we want to make sure that it's clear that you're looking at the cross section. Just like in the later problems here, you've got circles and hollow tubes, and you've got a circle removed from a square tube. That is the cross section. So we are essentially applying our force into and out of the page. When we're putting this in tension, we're pulling on the cross section that we see. So we're not pulling from the sides or anything like that. Don't make the mistake of thinking we're pulling 230 kips side to side here, 250 kips side to side. It's 250 kips spread out over this cross-sectional area. So I'd make sure if you see a problem similar to that, that you're clear on what the cross-sectional area is. Now, problem 2, all about shear stress. So shear stress, same basic equation. The force that we're applying spread out over the area that's resisting that force. The difference in shear is that we're cutting across the area rather than pulling the area apart. So here we've got two plates, and this is kind of similar, I think, to one of the homework assignment questions where you're figuring out the stress if we could glue these plates together, make use of every square inch of that contact area in the lap joint, or if we replaced it with, replaced that lap joint, or we supplied it with 3/16 diameter rivets instead of glue. Now, be careful here. This was I saw a couple errors on the homework assignment where people were going a little quick and not really thinking about what they were doing. Some people read statements like this where it said 23/16 and read that as a 20 and 3/16 inch diameter rivet was used instead of glue. Now, that's not going to have the same area as 20 3/16 inch diameter rivets. It's also not physically possible to fit in the overlap dimension. I don't think this one doesn't tell you what the overlap dimension is, but on the homework assignment, I did, and it was, I think, 1.6 inches of overlap. You're not using a 10-inch diameter rivet on that. That can't work. So it was 10 1/8-inch diameter rivets, not 10 and 1/8-inch diameter. So be careful reading that. If they meant the fractional part to go with the number, there'd be a dash in between the two. So be clear on whether you're talking about diameter or whether you're talking about number of rivets. And I think there's a problem probably similar to that on the exam. And I think I may have changed the wording to make sure that it was clear that it wasn't 20 and 3/16 inch. So I tried to make that a little more specific. And then C is actually more of a design problem, a little bit closer to what we talked about last week, where they're asking you how many rivets are you going to need to support that joint. So, and that's a little closer to what we have on our current homework assignment. So here you've got to figure out what area do I need to handle this force. If you've got 1,000 kips of force applied, and the rivets have a maximum shear stress of 750 ksi, that should tell you about how much maximum stress you need. Let's go over to the board here, and we'll take a look at that. Let's see here. Oops. Let's try that here. All right, let's see. All right, hang on one second. I'm having a bit of a problem with my display. Let's try it this way. Nope. Where's view? Ah, there we go. Nope, that's not it. I'm not finding the option right now at this time. Let's see. There we are. There. Now I got my camera primary there. All right, so there we go. So let's take a look at the problem here. So the problem was we have a special rivet that has a shear strength, a max shear strength was 750 ksi, which is a pretty high max shear stress. 750 ksi is about 10 times more than some of the typical materials out there. We're supporting a load of 1,000 kips. So the load is 1,000 kips. That's 1,000,000 pounds. 1,000 pounds. So that's 1,000,000 pounds. And we want to find out how many rivets we need. So the typical equation, the basic equation to run to here, is the definition of shear stress. Shear stress is force divided by area. Normally we use this to figure out the shear stress. We know how much force we're applying, we know the area, so we find the shear stress. In this problem, we're turning this around. We're trying to figure out the area, knowing how much force we need to support, and knowing what the limit is on our shear stress. That'll tell us an area. So we can plug in what we know. We need to find out what area will just put us on the edge of failing. And that's going to be 750 KSI. We've got 1,000 kips, but we don't know how much area we need. So we'd cross multiply and solve that, and the area would come out to be 1,000 divided by 750. So we need an area of 1.3333 square inches, where I've kept 5 sig figs just for good measure. Now they told us here in the problem that we're looking for how many 3/16 diameter rivets. So 3/16 inch diameter rivets. So how many 3/16 inch diameter rivets we need? To figure that out, we need to know the area for one rivet. And since the rivets are circular, have a circular cross section, it would be pi times the radius squared. So it would be pi times 3/32. Be sure to stay clear on diameter versus radius. We may spec out rivets in diameter, but we end up doing radius calculations for the area. So 3/32, we'd square that and multiply it by pi. So the area of one rivet is 0.02761 square inches. Again, keeping 5 sig figs. So the number of rivets is going to be the area we need divided by the area of one rivet. And if we divide those two, we get 48.29 rivets. Now you can't have 0.29 of a rivet, but you've got to be careful, make sure you consider what direction you need to go. Do you round down to 48 or do you round up to 49? Well, the area here is the minimum area to get 750 KSI, to just stress stuff out, to just stress the material out to the maximum value. If we go with a slightly smaller area by rounding this down, we're going to overstress the material. It's going to shear out. So we need to go more. When you're doing rivet calculations, we'd always go to more. That will keep things below that shear stress limit. So we'd say 49 rivets in that particular example. So that was the second problem on shear and shear stress. Problem 3 is an elongation problem on this one. So this brings in figuring out how much length a piece of material is going to gain when you apply a force to it. And to recall here what you need to figure that out, we need basically 3 steps in the chain. We first find the shear stress, or the normal stress in this case, since we only have elongation in normal stress. So we'd have to find the normal stress from the force applied and the cross-sectional area. Then we can figure out, once we know the stress, we can figure out the strain. Essentially, finding the stress lets us jump into the material and figure out how much force there is on each square inch. That force on each square inch we can figure out from the strain, from the stress, we can figure out the strain by using the Young's modulus. So the area here, that comes from geometry. size and shape, areas, cross sections, things like that. The modulus comes from the material. And the strain tells us how many inches per inch, or how many feet per feet, or how many meters per meter the material grows by. We can then find the elongation by applying that strain to every unit of length. So again, we end up using geometry. And this was that loop that I discussed when we first started looking at this. We use geometry to jump into the material. We do a material calculation, and then we use geometry again to jump out of the material and look at the overall effect. So let's take a look at that problem. So here you've got three different situations. These are all the same material. They tell us the modulus of elasticity is 54,971 KSI. That was the tail number of the airplane I soloed in, by the way. It's 163 inches long, and we're putting a load of 60 kips. So our force is 60 kips. Our material, which only comes in here through the Young's modulus, is 54,971 KSI. Everything else is about finding the area. So you've got, because you need that geometry to jump into the material, we got to find the normal stress, and we need an area. And each one of these is going to have a different normal stress, and therefore a different strain and elongation. But the material is the same in each one. So let's just take the first one. First one, we got a rectangular cross-section bar. It's 4 inches high and 1 inch wide. We are also given the length. The length is the same for each one. It's 163 inches long. No special significance to that number. In the first case here, we've got a cross-sectional beam, or a rectangular cross-section bar, 4 inches high, 1 inch wide. So that's 4 square inches. So let's see how that would work out. So first we have to find the stress. So stress is force divided by area. We're applying a load of 60 kips across 4 square inches. So 60 divided by 4, that should be 15 kips per square inch. Now we do run into a little bit of a material problem here. It's not clear whether 15 kips per square inch or 15 KSI is below the limit for this material. Now, since you're not given any information to be able to look that up, you have to assume it is, or you can't go on with the problem. But in reality, I'd have to worry looking at 15 KSI. I'd have to say, well, is this within the yield strength of the material? Is it within the proportional limit where these equations work? If it isn't, if my proportional limit is 12 KSI, then I can't really use this calculation. It's too much stress. But to proceed with this calculation, we need to assume that we're below those critical limits. So we have 15 KSI there. With the knowing the 15 KSI, so that answers how much stress is on the material, we can go to our Hooke's law. Strain is the stress divided by the Young's modulus. So we have 15 KSI divided by 54971 KSI. In fact, that airplane's still around. I just flew in it a couple months ago. So 54,971 KSI. Now, important thing to remember here is to make sure you've got the same units. Sometimes they'll specify Young's modulus in MSI. They might say 54.971 MSI. If you ignore the units and just plug in the numbers, you're going to end up with a value that's 1,000 times bigger than you expect it to be. If you've got kips, if you've got KSI in one, you've got to have KSI in the other. If you've got pounds, if you've got PSI over here, you got to have PSI in the other. So if instead of 60 kips, they said 60,000 pounds, your stress you might find as 15,000 pounds per square inch. You'd have to convert that to KSI if you want to use your Young's modulus in KSI. So those have to be consistent. Very easy place to get off by a factor of 1,000. So we take 15 and we divide it by 5, 4, 9, or 7, 1. And we get a little more than 2/10,000ths of an inch, 0.000002728.7. And that's inches per inch or feet per feet or yard per yard. It doesn't make any difference. It's a proportionality. It's saying how much each piece stretches out by, essentially in a percentage. Now to find the elongation, that's where we use the length. And here it really doesn't matter what the units are. If they give you inches, you'll get an answer in inches. If they gave you feet, you'll get an answer in feet. And several people did that on the homework assignment. That was fine. Where I said the length was 12 feet or something like that. You can do an elongation in feet. Whatever units you plug in, you'll get out. That's the nature of the proportionality that is the strain. So we multiply the strain times the length. So we would have 0.0002728.7 times 163 inches. And that'll give us our elongation, 163. So it looks like about 44 thousandths of an inch, 0.0445, if we round it off to 3 sig figs there, inches. So a little more than 44 thousandths of an inch. Not too bad over 163 inches. And the rest of it would go similarly, be the same kind of procedure. Literally, the most difficult part of this should be finding the areas and using the right units, making sure your units are consistent. In problem 4 is probably the trickiest one on the exam. And this one is, I tried to give some notes to help out on that one down here. And all you really need is the cylinder surface area. When you're dealing with shear stresses, so this is a punch that's punching a hole. It's a knockout punch. It's used to make knockouts in electrical boxes and even instrument panels, things like that. Here you've got 60 thousandths inch 6061 T6 with an ultimate shear stress of 27 KSI. And you want to find out how much force it takes. How hard are you going to have to push down to shear through this material? Think about using the sheet metal shear. When you use the sheet metal shear, you have a blade come down that pushes on the material. What it really does is starts a little crack, and it causes that crack to propagate across the area of the material. We're doing essentially the same thing here, except we're poking a hole, we're punching a hole. So what we have to do is we have to figure out, the same way we do with all the other shear stress calculations, to find the area resisting the shear, we have to figure out, we have to think about what it would look like broken. After it's done, what is the area that's been exposed? If you're using a rivet and you shear through that rivet, you've got that circular area of the rivet exposed. Here, what we've got left over in a hole is we've got exposed material along the perimeter of that hole. We have a cylinder surface area. So here they tell us we're dealing with a diameter. The material, all this material in between these dashed lines, the hidden lines that are shown here, all that material in between is what was resisting being punched through. So shear stress, go back over to the display here, shear stress is force applied divided by area. Now we know what shear stress we need. We need, according to this material, for 6061 T6, our max shear stress is 27 KSI. So we have to achieve that shear stress with some amount of force. We know the area, though. The area is a cylinder, and I'm going to try to sketch that cylinder, kind of the plug that is removed, going to kind of look something like that. The area that broke is all that area around the outside. Well, this thing has a diameter of 3 inches, and it has a height of the thickness of the sheet metal, 60 thousandths of an inch. So this is 60 thousandths thick. Well, we can find the area here, and the equation I gave you was the surface area, which is the area that was resisting shear. When this punches through, that's the area that we expose. It's 2 pi times the radius times the height. So we have 2 pi times our radius, 1.5 inches, times our height of 60 thousandths of an inch. That'll give us an area. Inches times inches will give us square inches. So we've got 2 times pi times the radius, 1.5 inches, times the height, 0.060. And let's see here. Looks like that comes out to be just a little above half a square inch, 0.56549 square inches. So that's the area we've got to deal with. So unlike the rivet problem that we saw a little bit earlier in the exam, where we knew the force and we needed the area to figure out what would max things out, here we know the area and we've got to set the force. So we go to our equation. The shear stress we're looking for is 27 KSI. We need to cause at least 27 KSI of force, of shear stress, to get this thing to shear through. We're dealing with an area of 0.56549 square inches. And we're looking for the force. So we'd cross multiply, and that'll give us a force of 15.268 kips, because it's a KSI, a kip per square inch, times square inches. So it'd be a force of 15.268 kips, a little more than 15,000 pounds to do that. Now that's a lot of force. And in reality, that's not what we'd actually use. That would be what we'd need if we had a kind of flat cylindrical punch that we're trying to force through. Real punches don't look like that. Real punches, just like the shear, have a pointed portion, or have a portion where they concentrate all their force on one part and then lead that crack around. In a shear, in a sheet metal shear, for example, this is the piece of sheet metal we're shearing. We don't make a blade come down straight across the part. Instead, we angle that blade. And so it hits the corner first, and it concentrates its force on a much smaller area. We max out that shear stress there, and it breaks there, and then we lead across the part. So we have some things that we could do to improve this tool to a point where it could be done by hand. By hand, you're not applying 15.268 KSI. In a hydraulic drop forge or something like that, in a hydraulic press, you could certainly do that for 15,000 pounds, but not by hand. So that was problem number 4. And problem number 5, very similar to what we have on our homework assignment for homework 10. Here you've got a beam deflection problem. You've got a simply supported beam where we have pin support and a roller support at one end. We've got a load right in the middle, and we've got a cross section of this beam. They tell us what the moment of inertia is, and we need to find the max deflection. Well, this is basically just a plug and chug problem. You've got the equation, and I'd strongly encourage you to look at the last lecture and pull the 2 equations out of there for beam deflection. We had a couple different ones to look at. If we go back to that lecture set here, let's jump to that because I do have that up here. That's actually in this set right here. We have our beams, deflection of beams for a simply supported beam. We have the equation FL cubed over 48 EI. So max deflection for simply supported is FL cubed over 48 EI. And max deflection for a cantilever, which is what's on the next page, the cantilevered beam, is similar, FL cubed, but it's over 3 EI. We get 16 times more deflection. So those are our two equations. And I would encourage you to have those down on an index card somewhere, maybe even with the picture of what a simply supported beam looks like and what a cantilever beam looks like. Well, here we've got a simply supported beam, so we don't need the cantilever equation. We're dealing with FL cubed over 48 EI. And the only real trick to this problem is making sure you get the right units. So we've got to plug in the right units. So here we've got a modulus of elasticity of 15,000 KSI. We've got a moment of inertia. And if you're not quite clear on the concept of a moment of inertia, go check out the last lecture, last Wednesday's lecture. That has description of what moment of inertia is. We've got a length, and be careful there. It's length end to end that we worry about for these problems. So it's a 40-inch length. And we've got an applied force of 10 kips. And we want to find out the max deflection. So to find out the max deflection, we plug into the equation. You got to make sure that your force and your modulus share the same units. So you've got to have, if you have kips for the force, you got to have KSI for the modulus. If you have pounds for the force, you've got to have PSI for the modulus. Or you've got to turn your force from pounds into kips. So make sure those two line up, or you'll end up a factor of 1,000 off. The other thing you have to make sure of is the length has to basically be in inches. This doesn't work in feet. If you plug in feet, you end up with feet cubed, and then you've got inches to the fourth in the bottom, and they don't really cancel out. So you end up with factors of 12 and factors of 1728 off of the right answer. It's 12 cubed. So keep your lengths in inches. So I'd make a note off to the side here, lengths in inches, to make this one work. So if they gave you a length size in feet, you'd want to convert that to inches. Other than that, once the units are okay, you can just go ahead and plug things in. So our max deflection is going to be FL cubed. Well, F is 10 kips. L is 40 inches, and you don't even have to write the units down once you've got them consistent. Kips and KSI, inches and inches. Just focus on the order of operations and getting the number correct. So we have 48, 15,000, and the moment of inertia was 12.2. Only the 40 is cubed, so make sure you don't multiply by 10 and then 40 and cube the 10 in there too. You'll end up with something 1,000 times too big. So we have 10 times 40. The 40 is cubed, so we have 10 times 64,000. Up on top, we divide that by 48, by 15,000, and by 12.2. And we end up with a maximum deflection here of 0.0729 inches. So a little bit more than 72 thousandths of an inch. Well, 72 thousandths of an inch is about 5/64ths of an inch. It's about 2.5, 30 seconds of an inch. It's really not all that much. It's definitely not lots of inches. So it's well within the capability of this structure. So that was the beam deflection problem. Pretty straightforward. You can probably expect to see a beam deflection problem of one type or another, either a cantilevered beam or a simply supported beam. But definitely got to pay attention to those units. Have your basic equations down on your index card. Sample problems, if you've got room for it. You got 3 index cards you get to fill out for this one, and you might not need truss analysis and all that. You will not need truss analysis, I should say. So you can use those 3 cards for lots and lots of references. The only thing I wouldn't write down are material constants. I'll provide you with any of those that you need, just like I did in this exam. I don't expect you to tabulate every possible material on your reference cards. So that's pretty much it. Unless anyone has any other questions, I don't really have anything else formal for the evening.
No questions.
All right. Well, then have a good night, and I'll see you all Wednesday night.